Hello everyone. I'm sure all of you are doing awesome. So this is the second part of our OS fundamental series. In our first part, I hope you have checked that out before coming into this. So that is kind of a prerequisite to this video. So there we have covered what exactly a text segment, that is where the code is converted to machine executable instructions and how it resides in our operating system, and then at the time of executing that machine executable instructions, how stack frame, heap, everything comes together, why stack frame is necessary, and how a movement of a given program happens. Everything we covered in that video. So before going through this one, kindly check that one. That will keep your concepts very clear. And so here we are going to go way more deeper what we did in our last video, where we have gone through like how a program is converted to a process and how heap and stack comes together to execute it. So here we will come to the other concepts like stack. uh, Alongside stack heap, we will introduce like things like program counter, cache, register, pages, and how all of them come together to execute a simple program. Our approach will be similar to the previous video only. We are going to take a very simple program and we will try to see the end to it, how exactly it is being executed. And then we will go into the concepts like what exactly happens during segmentation fault, or whenever we now after getting all these concepts, whenever we see a simple null pointer exceptions, or a simple stack overflow exception, or anything else operating system related exception in our program flow, how can we actually know what is going in the internals? Okay, so here let's to get started with that, let's start with one concepts of the virtual address space, and we will try to see how virtual address space is used in our memory execution. That will be kind of the first step of this whole flow that is we are going to explore. So let's take example of this simple program. What this simple program is doing is, suppose you are one of the developer with the Airbnb, and through your company, your users are attempting to book a room, and as a company you are trying to charge the user. So what you are doing is, at first you are checking that is your room available. If not, you are returning false, and then you are going to charge the user. So there are some internal calls that are happening here, and then you are making a database call, or in some way in your data store you are making sure that your room ID is into a booked status now. So there is a main execution flow that is happening from book room, and then we are going into this 2 3 inside function calls to it. So before going into the next steps of the function executions, what we already know is from our previous discussion or our previous video, that this program is creates a process behind the scene. Like when we are running this whole program, there is a process that is being created. So in that process, whenever a process is being created, a very important concept here is virtual address space. Okay, so what exactly virtual address space is? So for each process, its own sandboxed virtual address space is being created. So that means if two processes are running, like P1, okay, so it will have a virtual address space 1, and if another program is running, suppose P2, it is going to have its own virtual address space 2. And interestingly, they don't know what is happening with each other until unless we do some inter-process communication. That is again a different concept, but here this virtual address space totally abstracts RAM. So if you see that if you imagine that these programs like P1 and P2, they are trying to access the, yeah, here comes the P1, and here comes P2, they are trying to access the RAM. So this doesn't happen directly. What is happen is, it has its own virtual address space that is created around it. So using this virtual address space, it uh, goes to RAM. So whatever the memory P1 is executing, P2 has no idea around it. So that is the OS's idea to abstract the thing. And this virtual address space, which maps to the physical memory, how it maps. So there is something called MMU, or memory management unit, memory management unit, that comes in play here. So MMU helps into that. How this whole translation happens, now we will go in now we are going to do a deep dive around this. So at first, let's understand what happens in this code. Okay, so suppose your web server, this program is running, and this program is I'm naming it as our hotel booking service. Okay, so instead of P1, let's mark it as like a hotel booking service. Okay, so there is this processes running in our OS. Okay, process in OS. Now suppose this is kind of a running as a web server. Okay, like the exactly like we discussed in our previous video. So when a request comes in there, okay, when a request comes in there in terms of book 101 123, something like that. Okay, so 123 is the user ID, as you can see over here, and 101 is the room ID. Then what starts happening, like this is a valid request, right? So what starts happening behind the scene? So at first, when this process is running, one of the things that happening there is, there is a all the functions that we are having, all the functions here, like the book room, is room available, charge user, and update room status, they have their own virtual address as well. So virtual address means this address, okay, this particular address helps us to determine where exactly in our memory, when I say memory, it's RAM, where exactly in our RAM the program is loaded. Okay, this or like the programs, this particular method or this particular part is being loaded. So this our program might take a lot of memory, but this particular method is residing on this particular virtual address space. Okay, and then using MMU we can convert and go to our RAM. So in this process also you see one concept here we have written, that is called program counter. Okay, so let's take a smaller portion of our code. Okay, so uh, we will just discuss what exactly a program counter is and how it operates with this. So this is a smaller portion of our code, and the thing that we know, this book room, it has a separate hex address. So b- because understanding or writing those hex addresses are difficult, so just imagine that book room is a certain place called memory A. Okay, or rather I would say virtual memory A, virtual address space VAS, virtual address space memory A. So now probably you got the understand the VAS memory and the RAM memory is different. So this is currently our program flow knows about that this virtual memory address A consisting of this book room where I need to execute something. Now let's understand how all these things comes together: instruction register, base pointer, stack pointer, and a program counter. So this stack, when we are talking about, let's think it as a stack trace, which we call like whenever we get an error. So this is the whole stack trace, and what exactly happening behind the scene, let's explore that. Okay, so whenever a function is being called, the top of the function is always maintained by the base pointer in that stack frame. So in that stack frame, using this base pointer, I know, okay, so let me write it there. Using base pointer, I know start of current functions stack frame. Okay, so the start of the current function stack frame I know via base pointer. Okay, so this is the idea of base pointer. And the moment this program comes inside this method, stack pointer keeps on moving. So what starts happening over there is this, in this part, stack pointer will keep on moving around all these things like is room available, charge user, and update room status. All this movement will happen via stack pointer, and base pointer here will keep the part when the where the book room entry happens. And where does it help? So when this program this method execution complete, it knows that in a last in first out data structure like stack, till what point I need to pop my data. So this is the main essence of how the program stack is maintained and how beautifully operating system make sure that the moment a stack pointer a stack pointer reaches end of this execution, how does it know till what point it will pop all its and it will go to its caller method. Let's take it in a little bit more detail to have it a to get it clarified. Then we will come into the instruction register and program counter. So the moment we are calling book room, okay, the moment we are calling book room function, so BP holds this memory, okay, base pointer holds this memory that we are entering into some memory address, suppose memory M1, okay. So BP holds this address that we are entering into book room method. Now this is one of the address within the stack frame. Everything is happening within the stack trace or stack frame, however you want to perceive it. Everything is happening within the stack frame, okay, within that execution. So now SP will start playing around it. So what SP will tell is ki, look, I know that you have, yeah, so SP will tell that my job is to move around the program, okay. So now stack pointer will tell that I am in the is room available, okay. So now what happens is this BP reference will be maintained, but BP now have to go inside the is room available. So now if I have to see this is room available, so this is room available is getting called from here, okay. So this is room available is getting called from here. So now as a next step, what will happen is is room available is getting called, and our BP will now start pointing to this is room available. Yeah, but before going into the is room available, let's mark this thing as stack frame 1, okay. So what happens in our main stack trace, suppose this stack frame 1 is staying at the bottom right now. Probably this book room is being called in multiple stack way, but let's take it as our current entry point, okay. So in our main stack, so in our main stack trace, what happens is this stack frame 1, this we will mark as a stack frame 1. We can't it will be difficult to fit all of these things, so I'm just marking this thing as stack frame 1, and this stack frame 1 will be put into here, okay. Now, when the next function call happens, what happens is a new stack frame again gets created. This is the main important point and a very essence of the OS execution. Just understand this. The all functions they share within a single flow a same stack memory region. Within that stack memory region, each function gets its own portion of stack used, which is being known as the stack frame. So whenever we are talking about the base pointer or the stack pointer, we are talking on the stack frame. So now when we are moving around this, what will happen is this will get the BP, the base pointer will now start pointing to our new memory region of is room available. Okay, suppose that is memory M2. Important part is, you see, already my stack is actually having this reference like till what BP has been executed, like what has been the entry point of the book room. Now I know that the entry point of the is room available is BP, and SP probably is currently in this if statement. Okay, this particular if statement that you see, the our stack pointer will be there, and here what will happen is for this stack frame we'll get a new BP. Okay, so here it will store that entering into is room available, and then again SP will keep on move around it, and what SP will tell that I am returning from here. Okay, I am returning from this room ID %2, and it will be it will return true or false. And on top of SF, suppose if I just treat this as SF2, if I just treat this as SF2, what will happen is now you see this SF2 will be out of the stack. So what SF2 does is SF2 will tell that look, I have executed myself, and what I have found is that it is returning based on my input what exactly I called over there, like book 101, right? So if room ID is %2, it is 0, so that means room are available, so this is a false we are going to return. So what SF will tell, SF2 will tell to the program execution stack that hey, I am returning false from here. Okay, and then SF2 will be removed from here. Okay, the moment this execution completed, SF2, it will be removed from here, and the program execution will now stop at SF1. Okay, and what will happen in SF1 is again it will the the stack pointer from here will start executing. So earlier what happened is stack pointer was pointing to here, now stack pointer will go to this one, and again another stack frame will be created. Instead of SF2 we are going to have another SF3. That SF3 will, so this SF3 that we are talking about, this SF3 will use charge user. Okay, so this SF3 will be navigating through charge user, and sorry, in this flow it will not even go to this charge user because it has already returned false. In case, okay, in case it SF2 return true, SF3 would have gone there into the charge user, and what would have happened is like SF2 is already gone this time, right? So now instead of SF2, SF3 will be there on top of this one. So again, once this part is completed, what will happen is we will go to the update room status. That will be another thing called SF4, and in this way the whole program will be executed, and at last what will happen is SF4 will also be cleared, because after the update room status, and when we are returning from here in this from the stack trace, the sf1 will also be cleared, so this stack will be free, and when the garbage collection happens, this stack will be completely taken out of the memory. So this is how the base pointer and stack pointer comes. Now you will tell me, dude, you have made two more statements there, like you will you said how the instruction register and program counter is also one of the very important part here, but you haven't mentioned anything around it. So let's explore that part now. So let's take program counter at first. Okay, so let's take program counter at first. So what happens with the program counter is, whenever I am standing a place in a stack pointer, how do I know where exactly I will go next? I will go next to get my CPU instruction. So this program is being loaded into our RAM, right? Now in our RAM, all these instructions is room available, and charge user, everything in a machine code readable way, everything is being aligned one by one. So how does my program counter would know that, okay, I'm done with the isroom? When I'm done with the isroom available, I will go to the charge user. Program counter helps us with that. So what program counter does is, it preemptively, it keep on track where exactly my it keep track where is the next memory location for my CPU instruction. Okay, so just understand this thing now, that instruction, yeah. So just understand this thing now, that whenever we are getting into one program execution flow, we are going to keep track of what is going to be our next statement, and that is where the program counter will move until and unless any big exceptions or anything comes. And program counter, um, sorry, stack pointer will move across that, and program counter will keep a track of that, that where the stack pointer will go. So we will go into program counter a little bit more detail into the other part of the video, but just understand at this point of level that this is where the base pointer, stack pointer, and program counter comes together. Now when stack pointer is in this line, okay, suppose stack pointer has to return true or false from here. So just concentrate on this line. Okay, so this particular line, it is nothing but, in some of the CPU register, it will go to some register level, and then it will execute it. So when I say registers, it is basically, just try to remember your microservices, sorry, not microservices, the microcontroller study that you did. Whatever the CPU architecture we have, whatever the base registers that we are having, in that particular registers, we have multiple commands like move, copy, add, jump, all those things. End of the day, any program statement that is being executed, they are being executed at the register level with these instructions. So where this instruction register comes in place, this instruction register is actually will take those values whatever we are passing, like this room id. It will be, again, suppose in a different memory location, it will put those room id, it will load that room id, and it will try to execute this logic, and based on that, this registers are going to return the data to you. So now probably you got the, like, on a 100 feet levels right now, you got the idea that how all of these things comes together: instruction register, base pointer, stack pointer, program counter, and they execute a simple program whatever we are seeing with the two levels of function calls. So again, base pointer will always held the entry point of any function, so that while popping it out, while popping my stack frames, I know till what point I will be popping out, and stack pointer is basically the movement of the program at each level, and program counter is tells the whole stack trace, or the whole stack frame, like where it can go next to get its next CPU instructions or next values. And instruction register is the place where this execution actually takes place on a very CPU architecture level, okay, on a microcontroller level, where this where our computer actually executes this instruction that is being done by the instruction registers. So this has been a heavy concept on OS, and uh, many core fundamentals are standing on this. So let's summarize it one more time, what we have learned so far. So this particular is room available, what happens is, at this particular moment when we are returning false, okay, so at this particular moment before returning false, BP is pointing to the is availables frame, okay, and SP is pointing to the bottom of the is availables frame. So when I say frame, that means a stack frame, okay. So this is basically the stack frame we are talking about, and the moment this return is being done, what happens is, our instruction register, this IR is nothing but the instruction registers, okay. So this is the movement of SPBP, and this is the register, okay. So our register is going to hold that value 0 or the false, how it is being interpreted inside the machine language. And during the return, what will happen is, at first this BP will be popped, okay. And what will happen is, the BP will now point to, or the base pointer will now point to the caller function, that is the bookrooms SP. And also this SP, sorry, the bookrooms BP will be our new base pointer, and our stack pointer will be the bookrooms frames stack pointer. So now this program will be completely moved out, and what will happen to our program counter is, our program counter will now jump to the next instruction set, like this charge user, okay. If it is returning, sorry, here so we are returning false. In case we are returning true, it will be on the charge user, and if it is false, then of course it will go it will go out from here, okay. It will keep on saying ki now the uh, what exactly will be the its caller place, our uh, what will be the next set of instruction it needs to follow to go back to its parent method. In case of false, it will, our PC will jump to that next instruction, okay. So now when program counter moves, does it point to the next CPU instruction, or where exactly it goes? So again, PC, like we discussed in little lesser details, so I will just write it down to formally conclude. So it always, like the PC always points to the next CPU instruction to be executed, okay. CPU instruction to execute, and it is like a tour guide sort of a thing, which is keep on telling you ki go from here to there, okay. And it makes our microprocessor level registers work on move, copy, load, add, jump, all these things. All this all this machine instructions, it kind of holds, and it tells the stack pointer that keep on moving from here to there, okay. Now that you have this idea, let's take a real world exercise and try to understand what stack trace is. So if you have understood till this point, it will be crystal clear to you how stack traces are generated, okay. But still we will take an exercise. If you are confident, just pause this video and try to do a thought exercise around this program. Suppose this program is throwing an exception from here. Okay, then how would the stack trace, whole stack trace look like, and how as a developer we debug through it? It will be totally clear to you if you have understood till this point. But let's still take a example and have it have it have it in our mind, totally have it an end-to-end view in our mind. Okay, so the call stack or the stack trace is tracked by, there are three key players. We understood that, right? That is the SP, that is a stack pointer, base pointers, and also that is the return addresses, like what uh, what am I going to return from a certain level. Okay, so the stack traces are like the integral part of this are SP and BP. These are the primary things, and also the return addresses, they play a main role, that where I have to return after a certain execution or a stack frame execution. uh, a certain execution will return after the execution of a given stack frame. And very briefly, if I am speaking, suppose our method are being going from this level to that, like main to book room to is room available, and is room available, suppose there is some complicated logic which we are just returning false here. What will keep on happening is each level will have their own SPBP. Okay, and each level will have their own SPBP, all this calls. And suppose a certain exception is being thrown from this is room available. So suppose here is a certain exception is thrown, or a unhandled exception, I would say. Unhandled exception is thrown from here. So what will happen at that level? Our SPBP will be first returned, and of the level, like if I say this like a level 0 sort of a thing from here. Okay, so if I say that this is the level 1, and similarly suppose this is the level 2 of our caller. So SPBP of the level 1, then same SPBP of the level 2, level 2, and the SPBP of the level 3 will be returned. And interestingly, exactly it will return in this order, in which way it is being put into the stack, because it is in the stack. That is why the error, the actual error, we always see at the top of the actual error, we always see at the top of the stack trace. And that is why it is very important that we keep on logging our data at each level. Suppose user has reported that their is room available is being they are getting unhandled exceptions and their application is crashing. So now if you go to your log, you will see that what exactly has happened during that particular one. They have, of course, there is a stack trace that is being generated, and you need to log it somewhere, right? So it is not the user will copy paste from their own screen and give it to you. That is why logging is important, and we always keep on logging our stack traces. And from there, a programmer or a developer, they would generally go through and understand where exactly in the program flow something has gone wrong. Okay, so we already understood what is the role of a program counter. Suppose there is a, like if I just write a little bit of program in a more vanilla way here, all the programs that we were writing, let's take it in a little bit more vanilla way now. So in this book room, we have a console.writeLine. Console.writeLine is nothing but it is going to write into our console that you have hit a breakpoint here. Okay, so suppose I am setting up a breakpoint. Now what exactly will happen is, I will explain it with a text here. So this is our execution. Okay, and our debugger will be at the this line number 10, and inside this line number 10, what this console.writeLine does is it will call some internal functions which Microsoft .NET Stack holds, which is being known as like a write line function. And even my breakpoint is here. This statement is very important. Even my breakpoint is here. PC already executed a call instruction to get from where it can actually make this call. Okay, so now program counter already executed a call instruction inside the write line, and although it hasn't actually made the call, but it holds the memory address. So now whenever the stack pointer comes onto the next line, okay, suppose from this curly braces it is coming into this, at that point of time, it stack pointer is confident that if I go to PC, stack pointer knows that I'm going to get the actual memory instruction I will execute. Okay, so this is the role of program counter, which we already discussed. So although in this kind of execution, be it in Node.js, Java, Python, or any language, although your IDE shows that your breakpoint is here, but internally your program counter already have gone into those internal implementations and have taken their next CPU instruction address. So during this execution, there is a very popular methodology that is being like in our von Neumann architecture or in the computer architecture, and the operating system will come together and they perform, that is being known as fetch, decode, execute, and increment. Okay, so what this thing is, we will just go one by one and try to understand it. Okay, so fetch, decode, execute, and in increment cycle, it is a execution cycle of each CPU instruction. So here our CPU reads the next instruction from the memory, and the location is determined by the PC. Okay, and this instruction is being placed into the instruction register. So the CPU reads the next instruction and the location is provided by program counter. Now what happened in the decode is, during the decode, just after the fetch and before the decode, this instruction is being placed into the instruction registers. Okay, and instruction placed on register. Now that our register knows that there is an instruction, then in the decode phase, what internally those our CPU does is CPU interprets what does this instruction means. Okay, suppose I'm getting a given instructions in a hex format, so what does this instruction mean? And once it gets that idea, it decides which memory register or components to be used here. Okay, and then in the execute, all the things like add, move, copy, jump, all these things that happens. And it once this execution happens, or during this execution, what happens is like there are arithmetic, logical unit, memory, everything comes together. Okay, and once this execution is being done, what happens is like our given register will hold that particular output, and our PC moves to the next instruction. So this is the fetch, decode, execute, increment is the CPU instruction part that happens. And why I was covering program counter before, because program counter is the heart of it. From the program counter only the CPU reads the location and then loads that instruction, then gradually it decodes, execute, and again it tells that PC, look, program counter, I'm done with my execution, so you can move into your next one. So PC moves there. So just a little bit raw example, don't worry about this things, these are just addresses like 0. So there is an instruction of add R0, that is the value at the register 0, and there is this bp plus 6 instruction that is being passed. So what it will do is, in the fetch cycle, the CPU is going to read the instruction of the program counter location, that is 1005, and it will tell that add this R0 BP6. Okay, so it understood that we have to add this value of B to R0, and then this load, it will load the value of BP6, BP plus 6, which is probably in this location during execute, and suppose the value is 3, and so the register 0 now will hold the value of 8, and it will signal to the program counter that I am done, and then our uh, then our program counter will be going to its next location. So this is just a simple add. This is just a simple add, how it is being executed behind the scene. Okay, now after looking all these things, you might tell ki hey man, I understand what is happening till this point, but I but you promised us that you are going to tell us how all these things come together, like our stack, heap, RAM, program counter, cache register, and pages. So there are a lot of things you haven't touched. Like you haven't touched what is happening with the cache or the stack heap. You haven't even put together with it, or even the pages. So now let's go into all those concepts one by one. I was just trying to incrementally build the understanding. That is why I was going in this direction. Okay, so let's take another program, and we are going to break it step by step instead of going to the theory. Okay, so this is, suppose, another program. Let me increase it for you, the visibility. I think it is, yeah, I think, yeah, it is visible to you. So what this does is, it does the same thing, but at the same time it executes a little bit more logic. Like during the book room, it iterates through all the rooms, and it tries to assign, whenever a certain room is available, it tries to assign that particular room there. Okay, so where each memory is used, let's try to understand in this program. Okay, so when this program starts, suppose loaded into the memory, what happens is, so code is loaded and from HDD. Okay, suppose there is a dynamic link library or something is there for this particular code, and from hard disk this part is being loaded. So now what happens is, the OS loads its program code or the instructions from disk to the RAM. Okay, because this program is started, program is loaded from disk to RAM. Okay, this instruction includes all these things like main, book room, calculate total, all these methods, and in a machine readable way it is being loaded into our RAM now. Now if you are running this from an SSD, probably it will take a little bit more time, so a little bit less time. So hard disk drive, of course, slower than solid state disks, so it will take SSD will take lesser time. So that is why the HDD and SSD or SSD will come together here. And then what happens is, at the next level the execution of a flow begins. Okay, so what happens, instructions fetched into CPU caches and registers. Okay, instructions fetched into CPU caches and registers. And who is responsible for it? You know, the program counter is responsible for it using PC. Okay, so using PC, what happens is, these instructions are fetched into cache and the registers from our RAM. The instructions like booking of a book room 100, like as we see booking book room 101, are fetched into RAM, and how they traveled is, they get into different kind of caches. So suppose you have three level of caches in our program. One is the L3 cache, another one is the L2 cache, and another one is L1 cache. Okay, and then executed. So frequently used instructions stay in cache and rarely used ones may get affected. Why? That is the principles of LFU or LRU, that is the least frequently used or the least reused units will be they will be maintaining into the cache. Okay, so here we are talking about that any instruction that comes, if it is a if it is a very much used instruction, then it will remain on the cache. Okay, so now what the flow is from the RAM, the datas are coming into this caches, and from those caches what happens is then they go into the registers. So now that we know all the concepts already, what happens in the registers, so I'm not going into that details of the registers, but let's try to see how stack heap and the other thing comes together here. So now here you see we have created a new object. Okay, whenever an object allocation happens, object allocation for a given for a given class object happens, a new object is created into the heap memory. So look, all this program is loaded into our cache, but what happens is this object allocation goes into the RAM, okay, which is being known as the heap memory. And this array of book rooms that you see over here in this private int, this is also stored into the heap memory. So anything that is part onto the object, okay, so the object allocation and its properties are now stored in heap. Okay, and the array booked room, whenever it is first time accessed, suppose I am getting this value in a iterative manner, okay, then what happens is this values, this book room I, for example booked room 0, okay, it will again travel to RAM, to cache, and during execution to register. Okay, so here we are waiting in this loop, right? So what happens here is book room 0 is now residing onto the register, and then when it comes to the next, when it comes to the book room 1, how CPU looks into it from the register, when the operation is being done, again it will be moved to cache, and when book room 1 will be tried to access, what will happen, at first we are going to see the L1, then L1 is the fastest one, then we are going to see the L2 cache and then the L3 cache. If not, then we are going to check it from the RAM, and from the RAM the value will be again traveling to the cache and the register. So the moment again um, the register access is being done, it will reside in cache for some time. So suppose after, just right after this for loop, in some way we are trying to get into the book room, okay, and suppose this is storing into the L2 cache. So now I am trying to put something around the book room. I'm trying to update the book room for a certain user to a given room ID. Okay, outside this for loop, after this line 23, suppose. Now what I'm going to see is, at first I'm going to see whether it is there in the L1 cache or not. Then I'm going to see in the L2, and from L2 the data will be returned, because currently the data was in L2, and suppose this is being the latest data, this is in the L1. Okay, so here whenever we are missing some data in L2 or L1, this part is being known as, the popular term which we keep on using as, cache miss. So this cache miss of course have some kind of a micro or nanosecond sort of a overhead. So although but in the program flow it makes sense, because once you are done in at the time of execution, maybe you are moving or you are gathering too much information around this around those variables. So putting them into the cache makes sense, although there is a chance of cache hit. And once it is being not used for a certain given time, what our operating system does is it keep on emptying from the cache completely. Okay, and if the program is anyway taken out from the RAM, if the execution is stopped, then so from the RAM and the cache, from everywhere we will take it out. Okay, so in this process, once something is being taken from like L1, L2, L3, then it will be placed to registered as we understand. Suppose now I have a very big array. Okay, uh, like 1 MB. 1 MB array, will it fit into L1 cache? So the answer is no. Like a big array or a big size image I am processing. Okay, will it fit into L1? The answer is no, because this L1 has a very less capacity. So what happens is, in these cases, our array gets splitted into gets splitted into, and this OS strategies are being completely controlled by the operating system itself. And what it does is, it will split into multiple forms or multiple small arrays, and it will keep on putting it into L2, L3, and there are some other strategies can also be there. Suppose one array element is changed, then what happens is, because this thing was coming from RAM, okay, and stored. Okay, so this is one of the case that I wanted to highlight. And one more case, suppose what happens when some element is updated. So what is the criticality of it? Look, from RAM I am taking one array. Okay, I am taking one array, and this array I am storing it in cache, and from cache I am taking it to the memory register. Okay, now suppose the memory register changes to the array 0 to something else. Okay, suppose some value is there, and now, so as the data is being served from the cache, how does my RAM knows this thing, that this cache is being like this particular array is being updated? So in this process, what happens is, there is a dirty flag that is being maintained. So when an array element is changed, we write back to cache first, and we mark this value as dirty. So whenever we mark something as a dirty, that means it has to be read from the cache until unless we are syncing it back. Okay, so once this data come into the cache, once the data updated, we mark the data as dirty, and then we put a signal to the RAM that because this is the dirty data, you do not have the latest data, so please update it. Okay, and then it is being synced to the RAM. So these are two very important, or two or three very important concepts in this. What exactly happened during the cache hit or cache miss? What happens for a um, uh, very big array when it is being moving across the memory to the register? And what happens when an update happens to a given element? Like, how does it is being relayed back to RAM? The last answer is like through the uh, through this is dirty flag. Okay, now one of the important thing for the computer science engineer is like understand a little bit regarding the hierarchies. The time is not important, but just have it always in mind during writing our code or optimizing our implementation, that although this registers and cache, these things are not exactly in our hand, but the register is definitely the fastest one. It works in 0.1 nanoseconds, and it is managed by the compiler CPU. And things that is in the hardware, that is the hot code that is on that particular code, on that particular moment, that is being executed, that is being put into L1 cache. And these are like some less frequent data, and the shared data will be in the L2 and L3. And in the RAM, all the objects or the stack will be there, and the disk is definitely the main. Even before loading all the objects and stack, the DLL or the dynamic link libraries of those programs are being put into the disk. So now you understand why like the IO operations and file operations are expensive, because IO operations or the file operation happens in this level and they have to be bought up into memory. Like any file operation that happens, gradually they have to bought up into the memory, then the cache, then the register, and after the execution happens, then again you have to travel back to all this level and write to the disk. So that is why whenever we are doing a file operation, like saving something in a file is way more expensive than having some in-memory data and operating on that. That is where like we use things like Redis. Redis is a in-memory data structure that happens in the RAM and the cache level. And whenever we are going into any persistent data storage like our database or anything, look, this much amount of uh, this much amount of speed difference happens. And also one more important thing in this thing is like our RAM or our cache or our HDD, they can persist the data. Okay, they can persist the data based on their time to live of those data are being given, but the registers they won't. Okay, so registers that just do the operations and tell key, okay, in this particular like register I'm holding this data and keep on returning this. Okay, so now just to summarize this part of our discussion, let's verbally cover this. So what happens is whenever we are loading a program from the disk, it goes from disk to the RAM, and when we start executing the instruction, it goes to the register, and uh, its data is being processed and the actual data are being executed there. And then whenever allocation happens, then the allocation of the booking object happens is in RAM, and when a certain frequently access happens, it happens in the cache. And whenever we are returning from a function, then our stack plus register are involved here, because register gives you the data to be returned, and whenever we are returning, it can generally happen via the cache. And important thing is written till it's hot. Like if it is not a new one, the whole thing, the looping over happen in the cache. And whenever any saving of result happens, it happens in the it happens in this way, like whenever a file system operation happens. Right now what we discussed, that like from IO or the disk operation, whenever those kind of operations are to be done. Now that we have covered all this thing in this detail, there are few other concepts which I want to put you as your homework. The one, it is just one Google search or one LLM chat GPT search away. What you do is you just go through few concepts like spatial locality, temporal locality in operating system. And although we discussed in very small detail what exactly is cache miss penalty and how it penalty and how does it affect the overhead in a execution. Okay, so you will probably now be able to start also appreciate why space complexity and time complexity, these things are so important topic. You, if you are just making like a unnecessary copy object, how many things happens behind the scene. Suppose you are taking a file object and you are making a copy in your memory, what kind of intensive thing the CPU has to do. Probably now after studying all these things you will start appreciating. Okay, so now the next point is whenever a process is running, that process have process doesn't have direct memory addresses to RAM, rather a virtual memory is created. Okay, so how this virtual memory and this interaction with RAM happens, let's do some deep dive on that in detail as well. So now let's do a deep dive into our virtual address space. So the statement that we did at the initial level is each process sees a virtual address space. It doesn't have any access to the direct access to the RAM. Okay, so virtual address space. So suppose this we can think as a like a kind of abstraction created by the OS, and What the virtual address does is, now a very important concepts that I'm going to introduce. The virtual address space is broken into equal size pages. Okay, it is broken into equal size pages, and who will maintain that which page refers to which memory in the RAM. So just understand, to explain my question in a more deeper way. Suppose you have this is our VAS. Okay, suppose we have this page 1, and inside that page 1 we have lot of addresses. So how our program would know that this particular page address, okay, this will refer to this actual memory address of the RAM. Okay, so virtual memory is now broken into pages. So behind the scene, OS maps these virtual addresses to physical memory using page tables. How page tables operates, we will definitely go into detail, but let's understand what exactly is a page. Okay, so the pages are like, there is a, okay, yeah, so there is a virtual address space. Okay, and they are being put into fixed size memory blocks, and these memory blocks are being known as pages. And likewise in physical RAM, there are frames. Okay, so equivalent to this is on the virtual address space. In the RAM side, we have frames of the same size. So suppose the fixed size memory blocks or the pages is of 4 KB each, and in our RAM also our frames will be 4 4 KB each. Okay, now let's understand how all of this thing come together, like the virtual memory MMU. So virtual memory MMU page tables, and also maybe somewhere around the CPU cache. How all these things comes in together, let's explore that. Okay, so suppose there is a given program is there. Let's understand on this route only, because in this way probably we will understand the whole flow what happens there. Okay, so there are variable a, b, and some are assigned to different virtual addresses in the into the stack. Okay, so when we are seeing this variables, they definitely have different virtual addresses. So a will have some address into our virtual address space, b is going to have some address into the virtual address space, and of course some is going to have another one, although it is a arithmetic operation. So storing of a equal to 5, what happens is, it will tell that write 5 to the stack's virtual address of this. So suppose this virtual address is something like 0xm1. Okay, although it is a big hex code, but I'm, for the simplicity, I'm just saying this instruction, what it will tell ki put this value 5 into this tag's virtual address. Okay, now what our memory management unit does is, our memory management unit will translate this will translate this 0 into m1 into our actual physical address. So it will tell ki, our memory management unit, it will come here and it will tell ki, look, I have translated, and what I have found is this 0x m1 is basically actually 2x r2 in our RAM. So this value will be written here. Okay, so although the instruction is to write into that virtual memory, but the MMU translate it by writing it there. Okay, now CPU in the same time writes it into the L1 cache, not directly into the RAM, and later it will be synced using the dirty reads. Okay, dirty reads or dirty writes with the is dirty flag. Now when that arithmetic operation a plus b happens, so for a and b similar kind of a thing happens for both. Now when a plus b this operation happens, again CPU fetches from virtual space to physical space to cache, and what it will do is it will fetches all the data from the cache now. Okay, it adds the value in the register and it will stores the value in that given register, which will transfer the value to the L1 cache. If this information is too much from you, so just understand, from this A, value of A and B will be retrieved from cache and placed in registers for process. And once the sum is being done, so from register it will come to the L1 or the fastest cache. Okay, so instructions are always stored in RAM. Step by step, what will happen is to get those instruction using virtual memory plus page table translations, and through that we are going to bring it out, and by putting into the register we are going to execute the whole thing. Now you might ask me, dude, you have already told about pages, but I don't see how pages are being useful here. Because all these things I see that only the virtual address space and the memory management unit, it helps in the translation, and in some way they come together and execute the program. Again, take a program example. Suppose we are running a super duper memory intensive program, and how can I like simulate? So suppose I am defining a array size. This is very funny actually, like a big array of 1 GB array size we are putting over here. Okay, so assuming a 4 byte integer is there, this whole array that you see, it is of size, that in the line number that I have initialized, it is of size 9. So program will be in the in the process while the program will be running. Now putting the whole array into the RAM would be definitely put a lot of pressure. Okay, but our program, if you see here, it is using size by 2. So that means I do not need the whole array. So although the array size is 1 GB, if we are running something like if we are processing something like size by 4, that means only 250 MB is required for this particular operation. So what will happen is we don't really want the whole program to come in play. Rather, only the hot segment of size by 2 or the size by 4, which will be required to be in our memory. And what will happen over here is this half of this array we are going to put in one of the pages. Okay, so suppose this is my virtual address space, and what we are going to do is the first half of the array, the CPU will utilize in this way. And who does all these things behind the scene? It is operating system and its executions only, it execution models only. And in the second half of the array will be stored in a different virtual address space. So this is the VAS we are talking about. Okay, so what will happen over here is that we can see that there are two separation around that. Now when the application, so here our application is running, and application will go to the operating system. Yeah, through the operating system it will go to RAM, and it will tell ki give me the memory page of this big array. Okay, if that particular big array is not present, it will, if that particular array we are unable to store in RAM, where exactly we can store it? So there comes a very good concepts with paging plus usage of the hard disk. That is, we can put few things from RAM to our hard disk as well. So because we are not using this second half of the data, what our operating system does is the second half will be in a hard disk, and only the first half of the array will be in the RAM. And whenever the second half is actually required, it will be swapped from that memory. The probably because I do not have that much of memory in my RAM, so some data will be swapped. It will be bring to the RAM, and then it will be processed by application. So that is why this part is known as the usage of virtual memory. Now a very important terminology here. So virtual address space and virtual memory are different. In many places, while going through many documentation of videos, I have seen people are using virtual memory for both of these things. But please understand, this is virtual address space and this is virtual memory. So virtual memory is basically the capability where you can use your hard disk as a extended RAM, but of course it has a cost because application is trying to hit the RAM, it is not getting the data, so some data needs to be swapped out from the RAM to get those virtual memory data in. Okay, so there are many things happens in between that. Once if the data is not found, if the data is not in RAM, a fault interrupt is being raised. Okay, a fault interrupt is being raised, and after that fault interrupt, it okay, I was spelling mistake. So this data is being written, data is loaded from disk to RAM. Okay, and then the execution is resumed. So in this whole process, just understand, when this thing is going, this application is in literally in a pause state. So that is why whenever we are declaring something of very big size, it is very important to understand the memory implication that our program might suffer, because probably the operating system will try to manage it in some way by placing it into a virtual memory and whatnot. But what will happen behind the scene is this will make our application very very dead slow. Okay, so just again to formally summarize what happens in this case for this big program. So this allocation of the big array happens, this happens in the RAM. So then operating system understood that we are only using a part of an array, so we are going to hold only the first half of the RAM, only the first half of the array in the RAM. The second half will be unused. So OS swaps out this one into our disk, that is being called as. So there is two important concepts we introduced here: page swap and virtual memory. So now this thing is being called as page swap. Okay, voice swaps out the unused page to the disk. So now probably you understand how paging is being helpful now. So whenever this kind of a big program happens, one, so we always have those compartmentalized thing that the pages are spreading across from here to there, but it is always easy for the operating system to swap out a part also from our program. Just think, if it was not paging, okay, if no paging was there, how would, if no paging was there, how would OS manage this swapping? Swapping would be literally impossible because OS wouldn't know which part of the page are not being used. Okay, or what are the part of the program that are not, we don't need. I do not really need that part, so that pages will be, can be completely kept into the virtual memory. So as you see, like when this step 4 happens, like the access of the swapped out memory, then our, in this process our program is actually paused, and because this is a memory intensive things, and probably for a 10 milliseconds program is paused, and then again it will be loaded from the disk. So many concepts have come here. Swapping, so just to summarize, swapping is how the operating system manages the memory when there is not enough RAM, and unused or the rarely used access memory are the candidates who are being moved to disk. And here this how pages become useful when, like, plus virtual memory, that is one more concept that we have introduced here. And when your program one of the key thing we have to understand as a developer or as a computer engineer, that when a program accesses the swapped out page, a page fault occurs, and handling a page fault means it is a disk IO, and which orders a magnitude slower than a RAM or the cache access, and that is why this thing's always known as kind of a cold start. Okay, so virtual memory is kind of a disk based RAM. Okay, and this disk based RAM is, of course, there is a cost to use it. It is not that okay, I have this extended disk of mine, so I'm going to use it as it is. Okay, now you might be wondering, like, okay, I understand all these concepts, but how are they actually relevant in our modern day computing? So in our modern day computing, let's take, I mean, all the cloud infrastructure per se. Okay, so when we are talking about cloud infrastructure, the first thing comes maybe a virtual machine or like the AWS EC2 instance. So if you just see what a EC2 instance does is, behind the scene, all the virtual memory, the page table, process isolation, everything it does, and of course the physical resources are being managed by something called hypervisor. But end of the day, this process runs, like how this process will run, how the stacks will grow, everything remains same. Okay, so be it something like EKS, like the where the Kubernetes cluster or the ECS or the containers run, just understand all these things are nothing but isolated processes in their host OSs, right? They so they manages everything internally through the concepts that we have been talking about. And if we are running uh, like a very disk intensive program or a memory intensive program, there is no technology in the world which can beat, like which can make a disk operation to like a nanosecond from our millisecond part. Okay, so if we are writing a bad program which is taking a lot of memory, our application is going to suffer, no matter how modern or how highly provisioned system we use. So, and no matter how abstracted any services seems, like be it Lambda, be it S3 DynamoDB, please understand it all boils down to the process, memory, and the CPU. Okay, so now that we are almost in the end of the video, let's try to conclude it with a couple of small thought exercises. Okay, so this program that you see, what we are doing over here is, there is this unsafe segment fault example, as you can see. So what we are doing over there is, like, we have created a pointer, and we are telling that pointer that you stored null memory address there. So I think we all know what pointer is. Pointer is nothing but the memory address. So interestingly, we are telling this program that your memory address, we are telling that your star pointer or the memory address is null. Okay, memory address is null. Now, then in the next line, what I am doing is, I am doing operation that in that memory address I am trying to put something as 42. What will happen is, it will give me a null pointer dereference or a um, segmentation fault error. And what happens there? Like, if you see, there is this virtual address space. There is this virtual address space. This virtual address space will be put this particular null into a unmapped memory. So we are trying to put this data into that unmapped memory. That is why this null pointer dereference is using. So next time you see something like a segmentation fault, this whole map will be clear in your mind that I'm getting a segmentation fault. That means something is wrong happening over there. Now let's try to understand when exactly stack overflow, something like a stack overflow uh, when stack overflow exception happens. So now I think you understand very clearly, a stack overflow exception happens when a call stack which keep on tracking the function call, it grows and grows and grows and runs out of memory. Okay, so when there is a too many nested function calls or a lot of memory that we are putting, or suppose recursion that is being going on, which is uh, keep on increasing, the stack size is kind of gets limited by the operating system to each program level, so that it doesn't really crashes the OS. So what happens is, instead of caching the OS, it crashes the program itself, and it throws a stack overflow exception. And I think it is quite clear to you now, like, even if I'm not explaining why this kind of exception happens. And then also there is like out of memory exception. So out of memory exception happens on the heap level, and stack overflow exception happens on the stack level. So these two are different, and probably now after this whole session, if you have gone through it, you have done a great job, and I think you understand those details, like what is the stack overflow exceptions, or what is the out of memory exception. Okay, so yeah, so now with this, I'd like to conclude this really long video. If you have made till this far, I think you have learned one or two new things for sure. And that's the video, guys. If you have any question, please put it in comment section. So see you in my next video. Stay awesome. Thanks a lot. Bye.